first thing I want to do is figure out these marginal utilities. So what do we have to do? Take derivatives, exactly. Ha. Right? So these are great. You'll see also why these this functional form is very useful and chosen. So if we take the derivative of u with respect to c, right, they're additively separable, c and n, so we can just look at that first term, and it's the easiest derivatives that we know. We just pull the exponent down and subtract 1 from the exponent. Right? So this is simply equal to 1 minus sigma over 1 minus sigma times ct 1 minus sigma minus 1. That cancels out, so we're left simply with ct minus sigma. The derivative with respect to nt, same thing, pull the exponent down, subtract 1 from the exponent, so this is 1 minus phi, 1 minus phi, and t 1, plus phi minus 1. That cancels, and this is equal to minus nt phi. All right, so for equation 10, we have minus unt over uct equals wt over pt equals minus is a plus, so we have nt phi over ct minus sigma. And then equation 11, qt equals beta et uc plus 1 uc p et over pt plus 1. And this equals then beta et, what this as ct plus 1 minus sigma ct minus sigma pt over pt plus 1, or we can write this then as beta et ct over ct plus 1 for power of sigma pt plus 1. Choose. Or there might be different ways, it's whether you want to keep these individual or maybe bring them together. This looks like, a consumption growth term. We saw this with the acid pricing. Sharp ratio discussion on the last lecture on Thursday. And now, let's think about log linearization. Right? I have a handout that I put up. There are a number of different ways you can do log linearization. And the textbook from Gali has a way. There's, I prefer the way that Howard Ruiz taught me. He's at the University of Chicago. But they all should be the same. The only kind of difficult thing is that we need to keep in mind is that some variables we want to keep, we want to do a log deviation from a percent or from a steady state. A log deviation from a steady state or from some point. All right, so we're going to think of maybe C hat t is the log deviation of CT from some reference value from steady state. Right, we can, the power of logs is this, which we can also then rewrite using that fantastic math trick that I love, add one, subtract one. And this allows us to express a variable in terms of log deviations from this reference value. Most of the time, this is the way we want to go. There's some times where it can be useful to think about this differently, or to do it differently. One example is, say, a variable that can be positive or negative. This is a problem. This log specification, if you think of investment can be positive, but you can be increasing your capital stock. When I retire, I will have negative investment. Right? I'm going to be living off my capital stock. I'm going to be decreasing my capital stock, negative investment. The log of E is 1. The log of 0, or the log of 1, I'm sorry, is 0. I know those two values of the natural logarithm. I don't know any others. But no, that's not true. I know two others. The log of infinity is infinity. Right? It's an increasing function. And the log of 0 is minus infinity. What happens if we go from E, that'd be 1, to 1, that's 0, down to 0, that's now minus infinity, and we want to go to the negative area, where we have investment perhaps being negative. The log of a negative number is imaginary. It's complex analysis. That's going to be a problem. Yeah? So for a variable that can be negative, it might be useful sometimes to think of, right, to not express this in terms of log deviations or percentage deviations from a steady state. Other variables are already perhaps expressed in terms of percentage points. If the interest rate is 10%, and I tell you the interest rate goes up by 10%, what's the interest rate? Is it 20%, or is it 10% of 10%, so 11%? Oh, yeah, that's kind of confusing. Percent of percent deviation, something that's a percent, is a problem. We want to think of this naturally in terms of percentage point changes. So that if I say the interest rate is 10% and it goes up by 10 percentage points, right, it's gone from 10 to 20%. Right, so it's actually doubled. It's increased by 100%, but by 10 percentage points. It's the natural way to think about that. And that's, we'll see in a second, that's what Jordi Galli likes to do, specifically with the interest rate, and express things, and also here, or relative, he does something different. What he likes to do is to not talk about the deviation from. Right, so that's the one third case, and that's the case we're looking at here, where this might be a problem, or might be difficult to comprehend, or not so intuitive, as if we're always used to thinking about a specific level. So if we're thinking about something like the interest rate, we're always used to thinking about the absolute level, right? 10% is the interest rate, or 20% is the interest rate. We're going to see or think, or if we've already seen it, there's some underlying natural rate of interest based on our impatience. So if our level of impatience, I think of the log of beta, or the log of beta can be related inversely to this, what we're going to see is rho would be the rate at which you would have to compensate us for our impatience. And if the interest rate is higher than that, then we'll want to save. If the interest rate is lower than that, right, then we'll want to borrow. So for our economic decision, it doesn't matter, but it matters, it's more important perhaps to think about the interest rate being greater or lower than this impatience level, and not whether it's positive or negative, which would be relative to a baseline of 0%. But as economists, and so when we're talking to policymakers, it's useful to tell them the actual interest rate, 5%, 10% interest, right? And not 2 percentage points above the natural impatience rate of interest. You're not going to convince, the chairman of the party who's working at the central bank when he's asking you a question, if you talk about the interest rate is 2 percentage points higher than the natural interest rate based on our inherent impatience. And he's going to look at you, what are you talking about, right? So it's useful for us to think about some variables just in their actual number values. And this we can get within here the logs. Just the log of I, of capital I would give us this lowercase I. Right, so we can think of, not capital, we can think of the gross rate of interest equals 1 plus IT. Right, so the principal and this interest rate on top of it. So if I invest 100,000 dong at 2%, then next year I will have 100,000 2 dong. I will have 1 times my 100,000 dong plus 2% times my 100,000 dong. So 1 plus I times the amount that I invest. So this gives us the gross rate of interest. Right, this is related to our IT would be the net of the principal. Right. So, it's important to think about this concept. It says if you can, you can convince a bank to charge you a 10% gross rate of interest for borrowing the money, that's fantastic. So if you give me 100,000 dong, I just have to give you 10,000 dong back in a year. No. We want 110% in a year. They want to see their dong, the original dong, back plus interest on top. No? And if we take then here, obviously then here the log of 1 plus IT, the same approximation that we have here, gives us then okay. So let me do some log linearization. And I'm going to do it then in two different ways. Basically, look at the different ways that I do. Look at the textbook. Look at the handout, and just find one way that works for you. And you know what? That's the right way. I'm going to do a couple of different ways to show you there are different ways to do it. People, depending, some people like to do a Taylor approximation because they think of it this way. Some people like to do the Uhlig trick that I'm also going to show you. Some people, we can do things a lot more quickly in this expression. So first thing to see, if you see something that really is entirely multiplicative, we can just take logs directly. So you can save ourselves time. So notice it's completely multiplicative. So we have, just take the log of this expression, log Wt minus log Pt equals phi log Nt plus this minus sigma log Ct in steady state. We're going to have log, let's call it steady state, these variables with a line over them. Take the difference between the two, and we get log of Wt minus the log W bar minus the log Pt minus the log of P bar equals phi times the log of Nt minus the log of N bar plus sigma times the log Ct minus the log of C bar. And just using this definition of a hat variable, a log deviation, sometimes and we're done. We've the observation here is that this equation, if it's completely multiplicative, it's already linear in the logarithms. So we don't have to log linearize it. It's already log linear. That's straightforward. You can also look at the alternative of the steps of Uhlig, which would be step 1. Replace with definition can solve for xt here, and this gives us that xt is equal to x bar e x hat of t. So replace with that definition. Collect e's, and 3 replace with approximation of e, whatever xt is equal approximately 1 plus xt. Where does this come from? Take the log of this, and you'll see it's the same as that thing. Okay? So it's applying this log approximation. Okay, so let's look at equation 11, and let's first start with just writing down the steady state. So n steady state. And a quick side note, cultural differences. There are a lot of most people around the world, especially like in the United States, would abbreviate steady state with SS. But people in Germany don't like to do that because SS was the name of like one of the secret police of the Nazis, right? So it's kind of like, right? And you don't want to be doing economics and talking about, So that's the reason why I do that. It's always, for a long time, when I was in Germany, they're very sensitive about this or this or that. So, Part of the interesting thing about different cultures is learning about different cultures' sensitivities. So in the steady state, we can just drop the t variables. So q bar and expectations, the steady state, is given by the point when all the variables are constant. Right, and we notice these c's and p's cancel out in a steady state, so we just have that q bar is equal to beta. Remember q, the log of q, or related to q, at the discount price today of something that pays out €1 1 year in the future is going to be inversely related to the interest rate. This is again connecting some steady state, some long rate of the interest with beta, this measure of impatience. That's called sort of the natural impatience level of the interest rate. All right. And so now then step one, I'm just going to replace every variable with its q bar, e, qt equals beta, et, what's that then? C bar, e minus sigma c hat, t plus 1 over c bar, e minus sigma c hat t times p bar, e hat pt over p bar, e t hat t plus 1. Then we can already cancel some things out, make our life a little easier. Write these steady states here. And then since q is equal to beta, we can cancel that out. And then I'm just going to collect all of the e's the exponentials on the right-hand side. E u hat t equals the expected value of E minus sigma c hat t plus 1. This is then going to be plus sigma c hat t plus p hat t minus p hat t plus 1.
Professor,
Yeah?
can you,
Oh, yeah.
and you can read
But then I can't write. I think I can't. Maybe.
yeah.
Oh, but I don't know. That's a good idea. All right. And so now for this first one here, now in step 3, on the left-hand side, x is now simply q. So we can write this as 1 plus q at t. And the right-hand side, x is now all of this. Right, so this is the 1 plus all of that. So 1 minus sigma c hat t plus 1 plus sigma c hat t plus p hat t minus p hat t plus 1. Right, and we have now on the left hand side 1, on the right hand side 1. So we have q hat t
T.
equals then sigma c hat t. We don't need to write the expectation of that. Minus sigma, we don't know tomorrow's consumption, or its log deviation from steady state, with the form expectations. Minus then et p hat t plus 1 minus p hat t. The reason why I'm keeping them together, this is the same as the log of pt plus 1 minus the log of pt. Right, that is
Inflation.
inflation. Yeah. The log difference between two variables is their growth rate. So it's the growth rate of prices, so that's inflation. And now we just have to deal with this Q. Write this then as CT equals ET C hat T plus 1. Is minus 1 over sigma minus Q hat T minus ET T plus 1. And now we want to think about this. Q hat T, correct in the front. We determined on Friday together that this discount price of a bond, so this is the price today of a bond that delivers one dong a year from now, that because of an arbitrage argument, has to be equal to 1 over 1 plus the nominal interest rate. Because if we invested if the interest rate is 10%, then investing 0.91 dong today at our 10% interest would give us 1 dong tomorrow, which is the payout that this bond is promising us. Right? So the price of this bond must be 0.91. Otherwise, we could arbitrage and borrow money from the bank and buy lots of this bond, or short sell this bond and put the money in the bank and make infinite risk-free. So now let's zoom tight. If we log linearize this, we can just take the log, so this is log of 1 minus the log of 1 plus it equals minus it. Because this is equal to 0, and this is approximately equal to it. And the log of u hat is equal to the log of beta. And we had a previous lecture that beta is equal to 1 over 1 plus a rate of time preference, which here is rho, rate of time preference. And so we get then that the log of beta equals, on the same steps as we had here, minus rho. Rho. So now then, all this stuff is there together. We get then that q at t is equal to minus it minus minus plus rho. Inserting that into there, we get then dt c hat t plus 1 minus 1 over sigma it minus et t plus 1 minus rho. So we've now got something about why are we log linearizing? Right? We're going to find that analyzing these models, solving these models, dealing with these models is going to be hard enough when everything's linear. If we did this in a nonlinear form, this might be, and most of the time will be, impossible. We're going to have to approximate at some point in time. So if we approximate now, put it in linear form, our lives will be a lot easier. 1 and 2, for the variables that we've expressed in log deviation, percentage deviation, we don't have to think about the unit of measure. Imagine if productivity goes up by 1%, and we say that output goes up by 2%. We have 1% in, 2% out. We have like a multiplier. We can see this right away. But if we say that the width of a transistor on our computer processing boards decreased by 1 nanometer, and our production of desks went down by 250 million units, but our production of laptops went up by 127 million units. I don't really know what's going on. I think nanometers going down on transistors means that we've increased, like, I think they're smaller, so they must be better, right? Fewer desks, but more computers. I don't know, maybe that means GDP went up. It becomes very difficult to interpret, to see what's going on. Right? Again, think of the Google Maps. We want to sharpen our mind by narrowing it. If we express things relative to what they were before, right, we talk about percentage change in, percentage change out, we can see things immediately, understand them immediately. If technology increases by 1% and output goes down by 1%, there must be some process that, I don't know, we can already start to think of economic reasons why. So perhaps one reason what could happen, if we have technology goes up and a lot of people then lose their jobs, they're replaced by machines, right? We end up producing perhaps less, but with a lot fewer laborers. So maybe this is then more effective on a for a company, right? It's saving a lot of money and it's making a higher profit, right? We can think of an economic story right away that's a lot more sensible than if we look at trying to connect the unit of measure of technology, maybe it's size of transistors, to all the different ways we measure production. Yep. Okay. So now that we've got sort of households going, let's take a look at our firms. All right, and this is the heart of the new Keynesian model. We can, like this sort of relationship, the Euler equation, we saw the consumption savings, right? We thought about then the real interest rate, which is the whole term in parentheses there. Right? For a labor-leisure trade-off, right, this would be, standard labor market model for households when we decide how much to work or how much to relax. The key for that's going to give us monetary policy here is going to be our firms that have the monopolistic competition, where they can set their price. Right? My product is different than yours. Right? They might be similar. They might be somewhat substitutable, but they're not perfectly substitutable. No? Right? Your Tom is good, but mine is better, so I can charge a higher price. If you don't have a lot of money, right? If they all cost the same, who prefers the instant noodles to freshly made noodles in a restaurant? Right? Anyone? No. If they cost exactly, so why do we sell? Why does there's that little store in the bottom of one of the dormitories where you can buy instant noodles? Why would you buy instant noodles if you like freshly made noodles better? Well, maybe it costs less. Is probably the first reason. Yeah? So this imperfect substitution, price differences, and then we add in the second component that prices tend to be sticky. Yeah? If the world really worked the way microeconomists tells us it should, a monopolist should set its price as a markup over marginal costs. Right, so whenever there's a change in its marginal costs, right, so if we're importing part of, if we have, if we have Szechuan pepper that we're importing from China, whenever the yuan dong exchange rate changes, we know that this is going to change the price of the Szechuan pepper that we use. So we should change our prices. Right? The different meals down at the canteen should have different prices, right? And that should change on a daily basis depending on which costs more to make. One might take longer. Someone has to work longer. That's an increased marginal cost. Some might have a more expensive ingredient than the other. Different marginal costs show a different price. But no, for whatever reason, they charge the same price for them. Maybe there's, right, there's some convenience part there, or customer relations. Think about that a second. There's another reason why we might also want to change our price. This would be if we're a monopolist, we're trying to maximize profits, and we understand people's demand function. Right? If is the canteen open now?
Yes.
Yeah. Is there a line right now, do you think? No. Because most classes take a break between 12 and 1, I'm guessing, right? Yeah. Right? So if you've studied some of your micro, you think of profit maximizing, the canteen should probably charge a lower price now, shouldn't it? Demand is low. Right? So maybe the canteen should charge a price now of 25,000 dong, and between 12 and 1, increase the price to 50,000 dollars. Right? What would that do? It would maximize its profits. Right? This would be maybe good from some perspective because they wouldn't have to do all this work concentrated right around the lunchtime. This would mean that somebody would say, hey, Professor Marigota, let's take an earlier break today so we can have a cheaper lunch today. So we'd take an earlier, we'd spread this work out. There wouldn't be a huge rush between 12 and 1. Some classes would break a little bit earlier, some a little bit later, but we don't do this. No? This is inefficient, and a lot of people would get kind of mad. No? Imagine if they started doing this. They could change the price at the canteen, I don't know, just based on the line. You can have like a machine, like a camera with AI that just counts how many people are on the line. And the more people are standing in line, the higher the price is for everyone who's buying it in the line. So you get in line, and then you notice more people are getting in behind you. That's making your lunch more expensive. You might get mad at the people getting in line behind you, but you're going to be really mad at the canteen people who came up with this idea. Even though it might be good economics, this makes people mad. We're sensitive to things like this. We like to have dependability. I mean, imagine you have, I'm going to eat lunch at the canteen today, so I have 35,000 dong in my pocket, and they raise the price to 36,000 dong. Oh, no lunch for you. Tough luck. You might get mad, yeah? Well, to heck with the canteen. I'm never going to do that canteen business again. I'll either go outside or I'll bring something to eat. I'm done. Yeah? It's costly, perhaps, to a restaurant to behave this way. It angers people. Sometimes, you have a printed menu in a place. And if you change the price, you might need to change the price in the menu. That costs something. Or, let's say you're coming up with a new product. Right? We have the new, you have VinFast, right, which makes cars, Vietnamese cars. How about VinPhone? The iPhone, we come with a VinPhone, right? So how much should we charge for that? What would you do, right? You'd run a market study. So look around, you see how much the iPhone costs, and then you'd start, interviewing people. So, I see that you have an iPhone, you really like the iPhone, but we're going to come up with a VinPhone. How much would you be willing to pay? Not as much as the iPhone? Okay, that's fine, but how much, right? You have to figure out the price we're going to charge for the VinPhone, right? Then next year or next month comes along. Should we change the price? Yeah, things have changed. How much should we charge? Oh, well, it took a lot of effort to go around and interview people, to do a market study, to figure out what the best price is. That's not something that we want to do, every month or every day or every second, even though micro would tell us we should be optimizing this price constantly. Right? But it costs something to change the price. We'll probably stick with the price, even though we know, we need to raise the price of our VinPhone. but we're going to wait till the end of the year and we'll run a new study and then we'll set the optimal price. Right? So even though if we see that we should be raising our price because the optimal price is going up, we stick with that price until it's maybe big enough that we make a large price jump. We're not changing the price of our bin phone constantly. And you'll notice there's some goods where this happens more often than other goods. Like, the price, well, actually I'm not sure, how about the price for gasoline here in Vietnam? Does this change when you go to a gas station to get gas? Is this the same price for a whole year? Does it stay constant? No, it changes every day. Okay. So that changes every day. The price of a meal at the canteen doesn't change every day. There's a difference between prices, between goods. And some goods we have very frequent price changes, and other goods we have less frequent price changes. And this is very typical, and it's the same in we have a lot of similarities in many different countries. Like service industries, like they sell food, but they sell a service at the canteen that's preparing the food. Right? Those tend to be very sticky prices. Right? They don't change all that often. Commodities, like gasoline or rice, they change very frequently. Right? So we have a whole bunch of different prices that are changing at different times and different frequencies. And we're going to put this together, this monopolistic power, right? So we can set our price. You can't just substitute my good for another good perfectly. Right? So if I raise my price, you might buy less of it, but you're still going to buy some of it. This monopolistic competition, with then this inability to change our price every single period. All right, so that we can focus on firms' this pricing decision. Right, that's why we also look at this epsilon. It's not product specific. It's going to be constant, the same across all products, capturing like the average amount of competitiveness in our economy. But it's not product specific. So the only thing that's going to make a product different, it's not because it's more or less substitutable. They're all the same. It's also not going to be because it's easier to produce, right, or uses less labor or more labor on the margin. No, the production functions for all of our products are going to be exactly the same. So really imagine, we have our economy is just making these washcloths in different colors. They're otherwise exactly the same. The only thing that's going to make them different for us when we're putting together our washcloth collection is the price. We're focusing on the effects of prices here. Okay, so we have a neoclassical production function. You can think of perhaps capital as being economic capital is fixed. It is in A. And so this A is going to be a measure of a technology shock, a productivity process. And NTI is going to be firm I's labor input. Right? We have this the power of 1 minus alpha. 1 minus alpha is the elasticity of the production function with respect to labor input. 1 minus alpha is going to be positive but less than 1. Right? Think of this as, just like our utility, we have positive but decreasing marginal product of labor. Right? You get that first worker in, the first worker produces a lot. The second worker also produces a lot, but sometimes bumps into the first worker. Right? So the second worker the first worker brings us this much additional production. The second worker brings us a lot of additional production, but not quite as much as the first one, because sometimes they bump into each other. The third worker brings us more production, but not as much as the first or second worker, because sometimes they bump into each other, or sometimes the machines are being used by the first two workers, so the third worker has to wait. The fourth worker also brings more production, but less than the three that came before us. More bumping in, more waiting time. Right? That's the logic that we have of this positive but decreasing marginal productivity of labor. Right? And yeah. All right, now firms producing this technology, we're going to assume that firms maximize profits. They understand the production function, right? They know 14. They also know equation 9. They know our demand functions. They know how price sensitive we are. Right? Apple knows what R epsilon is. It knows how much it can get away with increasing its price above the marginal cost. We'll think in a minute, maybe we can figure out what Apple thinks our epsilon is. Right? All you have to do, we'll see this in a minute, is what you think it costs Apple to produce one additional unit. Right, so what does it cost Apple to produce the new iPhone 17? Is that one coming out, right? And how much does it cost? And comparing those two numbers, we'll be able to figure out what Apple thinks our epsilon is with respect to Apple products. So this is something we can get to this number pretty quickly. Just like alpha, 1 minus alpha is going to give us, in competitive factor markets, labor's share of national income. So what share of income goes to the workers? And depending on the way the economy is set up, the remainder goes to the owners of capital. Right? And the economy here might be set up a little bit differently. Right? The owners of capital are, in the end, the people of Vietnam. Right? But you can still then just divide this at the point of a factory level, how much is going directly to the workers that work there, think of their wages, and then how much then later through the sale of the products and the like is generated that then goes to the state or the private owners, if they're private owners of the factory, that way. This is usually something that we can measure through the remuneration of the English word is, but paying the workers' wages and the managers and owners, be they individuals or state owners of the factory. Right, profits are not going to be zero because we have some monopolistic competition. I can charge a price that's higher than what it costs me because there's competition, but it's not perfect competition. My product is special. My product has a label on it. Maybe it has a piece of fruit with a bite missing in the back, right? It's special. Okay. Right, now, firms aren't going to choose to change their prices every single period. And the way we're going to motivate this with, say, a menu cost, right? You have to make a new menu. If you change your price, that's expensive. Or, right, wait a second, we live in a digital world. We don't have to worry about printing new menus, or that's not a big deal. I'll just, write a new number on my menu. Okay, but you still have to then figure out what this new price should be. Right? And conducting a study, like for our VinPhone, is expensive. And you don't want to do this. It's too expensive to do every single day. Or third, you might have a business within the service industry that's based on customer relations. If you change your price too often, you might upset your customers. Remember, spontaneous price increase to 36,000 dong. Some people can't afford lunch, they're angry, and decide to never come back to the canteen again. This has motivated the canteen to not change its prices too frequently, and to make sure they communicate it in advance somehow so people can plan. Right? And this is also important to combine together with our monopolistic competition, right? Because a firm might have a price that's too high, right? Which means it's going to lose some customers, it's not going to sell as much as it otherwise would, its profits are going to go down. But it won't go out of business, right? Its profits might go down, but it's still going to be able to pay its workers and continue to operate. Right? Its price might be too low, right? So it sells too much of its goods, right? But the price will still exceed marginal cost, so its profit might not be as high as it otherwise would be, but it's still going to turn a positive profit, it's still going to be able to pay its workers and pay its suppliers, but it's still going to exist. This is, well, theoretically, what's important if you write a model, as soon as a price changes, like in a perfectly competitive environment, if your price is too low, or too high, if it's one dong above the marginal cost, you sell nothing. So you have no revenue, no income, you can't pay your workers, and you go out of business. Right. Here, we don't have that problem. You know, technically, right, we have a world where your price can be wrong, and you can still survive as a business. This makes sense. I don't think most businesses that we know don't determine the optimal price with as much precision as we economists are going to do with our mathematical models. Right? Your parents, run a small business. You might know they make these choices kind of. They look at the expenses, they look at this, and then they have a gut feeling. No, but it should cost this amount. And they would set the price along those lines, and they would continue to operate. All right, and then we have our integral. Remember, this measurably infinite amount of firms is now going to help us here. Because we're going to make this decision of when to change your price or not to change your price. We're going to make a random choice. There's going to be a fraction of firms that get to choose their prices in any given period, 1 minus theta, and the remaining fraction, theta, keeps their prices unchanged. So theta is going to be the measure of our price rigidity or stickiness. As theta gets larger, then we have a larger fraction of our firms each period that don't change their prices. So we can think about the properties of these randomly selected firms. Imagine we had a world, or we had a model, where not all firms were the same. Maybe there's a big firm, one big firm and lots of little firms. It would make a difference whether one of the firms that was able to adjust its price was the big firm or not. The big firm is, bigger part of the economy, larger influence on. No, all of our firms are the same, and they're all so small that whether you get chosen or not isn't going to affect the price level. You have no influence on the economy. And more than that, let's think about what's going to happen in terms of the prices that we set. The firms that can adjust their prices, they face the same production function, they face the same demand function, or they're symmetric. They're going to choose the same price. If I'm chosen to adjust my price, I'm going to choose the same price. Well, that's kind of fantastic. We've now gone from an infinitely measurable set of firms on the interval 0 to 1, to now one fraction, 1 minus theta, of these firms are all going to choose the exact same price. So now we just have to figure out what's going to happen with the remaining fraction, theta. This first fraction, whatever this optimal price is, we're going to figure that out in a minute. We're all going to choose that price. Otherwise, completely symmetric, completely identical. Okay, what about this remaining fraction, theta? Well, they're going to keep their prices unchanged. So they're all going to keep the prices they had from last period. So this means we have to track each individual firm's price as it goes through time, right? And then there'll be, find the theta, and we're going to follow, no, it's simpler than that. There's an infinitely measurable set of firms in this fraction theta. Since it's chosen at random, it's going to be statistically a perfectly representative sample of the prices we had last period. And if we take a perfectly representative sample of prices from last period, take the average of that, that's going to give us the average price from last period, last period's price level. So now we've taken this universe of firms, an infinitely measurable set, and because of our really clever assumption of this measurable set of them being perfectly symmetric, we only need to know two things to determine this period's price level. What the price level was last period, because all of those firms together give us a perfectly representative sample, and the optimal price level this period. That's it. We've taken this infinity of firms and turned it into two numbers. Yeah? So that's pretty convenient. This perfectly representative sample, this is an idea, this is, so if you're trying to figure out we're trying to figure out what the price of our VIN phone should be. Yeah? So we're going to run some market studies. We're going to ask people, right, if they would be interested in buying a new phone, a VIN phone, and what they would be willing to pay for it. Right? Well, why don't we just ask one person and stop? Why do we ask different people? Why do we ask more than one person? I'm sorry? When you say I didn't understand,
we want to have all the population.
all the population, yeah. The same, yeah. So we want to make sure that everyone is represented. So we sell a phone, not just at the price that Alex Meyer-Goda would like to buy it, but at a price that would, work for most of the people here. Well, what would we do ideally if we didn't have to worry about time or money or costs? We would ask every single person in Vietnam, right? Then we would have the right answer, right? Ask everybody. That's difficult, isn't it? It would take a long time because there are at least, 20,000 people in Vietnam? No, 100 million, right? There are a lot of people here. Asking every single one is infeasible. So we want to ask a lot of people. Ideally, we would like to ask everybody, but we can't ask everybody. So we need to choose the people that we ask carefully. Right? So let's say we're going to ask 1,000 people. So a bad way to design this questionnaire, if we're going to ask 1,000 people, go down to District 1 and ask 1,000 people. And now we have the best price for all of Vietnam. That's not, no. I mean, District 1 doesn't exist anymore, right? Isn't it now this is now Ho Chi Minh City, and District 1 got put together with District 3 and District 5 into the Saigon ward or something like that? Is that, I think I've got it changing. But so, right, we've got to make sure that we have, it's important, but it's not the entire country. It's not even, of course, all of Ho Chi Minh City. So we want to make sure, maybe ask a couple people, right, in the Saigon ward. Ask some other people, right, in different cities. Ask some people that live in the countryside. We want to put these 1,000 people spread around the country so that we get as good of an approximation to asking all of the 100 million people as we possibly can. Right? That's the whole idea of why we want to spread these people out and not just ask people in one spot. The great thing about this integral approach that we have here is we're going to ask a portion, essentially, theta keeps their prices fixed. We're essentially running a poll, we're doing a market survey, we're asking a theta fraction of these firms what their price was yesterday to determine the average price level that we had yesterday. Or to determine what their average price is amongst them. The point is, that's not asking one person, that's not asking 1,000 people, because it's an infinite measure, we're asking an infinite number of people. Yeah? We get a perfect sample of this entire population. And then if we ask, we get a perfect sample of firms who kept their prices constant from last period, that's going to, on average, represent the average price level that we had last period. All right, we can think of then this sigma and how it relates to the average price. We'll come back to this average duration. Now that we're thinking about this random selection, right, this is what allows us to take this integral. So our price level, we have this sort of geometric averaging of the individual prices with the integrating to 0 and 1. But now, to determine this period's price level, we don't need to track every single firm. We know that we have one group that changes their price, and they're going to choose the optimal price that the firms would choose, and the other group is going to have, on average, last period's price level. So we now get rid of this integral. Fantastic. I like to take derivatives. I'm an economist. I don't like to do it backwards. I don't like to take integrals. That's hard. And our price level, instead of the integral, we now just have a fraction theta. Keeps their prices constant. This is a random selection, so it's a perfectly representative sample of last period's prices. We have, we asked one person, right, in every town, in every village, in every household, that it's perfectly representative. We know exactly, right, what to charge for our bin phone. We know exactly that the average price of the firms selected or not selected, or stuck with their old prices, is equal to the average price from last period. And the remaining firms choose their optimal price PT star. We don't know what that is yet. We've broken our price level into just these two components. And now we can already figure out where inflation is going to come from. Divide this through by PT minus 1 and rearrange a little bit, and we get equation 16. We have here, so where inflation comes from, or inflation on the left-hand side, and on the right-hand side we have the source of it. What's driving inflation? Well, in terms of variables, we see it's this price adjustment. Right, well, of course, prices are going to go up, we're going to have higher inflation. If those firms who can choose their prices choose a price adjustment over last period that's large. So not every firm's going to change its price, but if those firms who can change their prices double their prices, well, that means we have higher inflation than if those same firms only increase their prices by 1%. Right? So the size of this price adjustment, the price change, is going to be a driver of inflation. And the other main driver here is this 1 minus theta. Right? That's the selection, the fraction of firms that are chosen to adjust their prices. So again, let's think of the example. If those firms who can adjust their price choose to double their price, inflation in the economy is going to be large if most firms are able to choose their price and choose to double it. It'll be larger than if the fraction of firms who choose their prices is very low. Those firms who are allowed to choose, who are chosen to adjust, choose to double their prices, but only a small fraction of our firms are chosen. Well, so it's going to be a doubling of a very few amount of prices. So those prices that can adjust change by a lot, but overall, on average, the effectiveness on the price level is small. So we just have small inflation. So we need kind of two things to come together for a large inflation. We need to have those firms who are chosen to choose their prices choose a large adjustment, and there are a lot of these firms who are chosen to adjust their prices. These two parts come together. We can see the advantage of log linearization by doing an approximation here. So let's do the log approximation around the zero inflation steady state. Right. Here, I wrote the equation out in log. So this lowercase variables are the pi, that's the log of capital pi, the gross inflation, which, let me see over here somewhere. Here to there. Which is this lowercase pi, which is net of principal inflation. Right, and then take a first order approximation. So you'll see this is then yet a different method than one of these two. You can use either one of these here as well. Again, find whichever method makes the most sense for you. So this is then taking a first order Taylor approximation of both sides. So express it from the logs, then do a first order approximation. Right, so we have point and the slope times change. This gives us the line from the left hand side and then the line from the right hand side. Simplify and we get equation 18. Right? Inflation depends on the combination of these two components. A lot of firms changing their prices and the change that they're implementing being large. Now we just have to figure out what this optimal price change is, what the optimal price is. And we can either skip lunch and do it now, or we take our lunch break now, come back in an hour and get to it then. You know? I'm voting for lunch. I think you are too, right? Okay, so I'll see you.